Alright, let's get started. So how many were you in the last class? Yeah. So we finished Unit 2. So what topics did we talk about? Laces theory? Cutting and filling, yes. Balancing depth and longitudinal section. Right. So we looked at unlined canals, and now we are going to start a new unit. The unit in the syllabus, it's called waterlogging. And so the topics we are going to cover in this unit are, so in the last unit we looked at unlined canals. Now we are going to continue lining of the canals, and we are going to design lined canals. And then we are going to see briefly types of lining. Now, waterlogging, it's a small concept, so we are going to look at the types of drains as well. We are going to design the drains so that we don't have any waterlogging. So that concept of waterlogging we are going to look towards the end of the unit. But in between the design of lined canals and waterlogging, I also want to do some gradually varied flow. So where we are going to talk about flow profiles. Have you heard of flow profiles? Or gradually varied flow? Yes. And how about flow profile? So have you heard of this term, flow profiles? Have you heard of this? So you have done any computations of this in the previous course? Computations of gradually varied flow or flow profiles. Okay. So let's say this is bed, and then you have a drop. So what kind of flow profile would it be? So you can classify based on the slope. So if the slope is mild or steep, then we have three types: M1, M2, M3. These are the three different flow profiles. For mild slope and for steep slope, we have S1, S2, S3. Now, I want to bring this concept because we are designing canals, and let's say we have a river. And this is our main canal, and we have an off-taking canal or a branch canal. And you have to build, let's say you have to build a weir or any structure so that the water level rises and then flows into this. So now we are introducing a structure which is going to impact the flow in the river. So this would change the flow depth and how far this impact would be in the canal. So we are going to study that. So I think this would be more interesting than digging more into waterlogging. So I'm taking this route where we are going to look at gradually varied flow and do some computations. And you would also be using Excel or MATLAB. We will see how comfortable you are. And then the last topic would be design of drains. and my plan is to have about 5 to 6 lectures for this unit, and hopefully we will finish it before the mid-sem. But it will not be appearing in the mid-semester. So in the mid-semester, you will only have questions from unit 1 and 2, and this will be for the end semester. So rapidly varied flow, you might have also heard of. Rapidly, yes, spatially. Yes. How about culverts? You may have touched it, no? Design of culverts. Okay. Yeah. Alright. So I'm slightly playing with the syllabus of the unit myself because I'm trying to bring in the concepts which may be useful for your competitive exams. So waterlogging, there are not many questions from waterlogging, but you would be getting questions from these or culverts. So depending on time, we will try to incorporate design of culverts as well. So now let's start with this simple concept of lining. So lining is where we provide protection for the bed. So instead of allowing it to be just sediment, we are placing concrete or brick layers or tiles so that the sediment is not able to move. So essentially we are fixing the section of the channel so that there is no erosion or deposition happening in the canal. Now, what are the advantages of doing this? So one is seepage. Now, what could be the second? So controlling the sediment motion, so there is no erosion or deposition. And what are the consequences of this? So if there is no erosion or deposition, what is the advantage? So think of the water levels. So let's say there is deposition, then what happens to the water level? So this is the deposition and this is the flow. Yeah, so there could be overflow. If there is deposition, then the channel bed has increased in elevation, so then the flow may overflow on the sides of the canal. So we are preventing flooding. And what else? What about my wallet? So do I need to spend more money for maintenance or less money for maintenance? So, sorry? So for operation, we have to spend less money because the sediment is still, it's not moving, so we don't have to do any excavations or filling. what about the surface roughness? If we have lining, so if we have concrete or tiles, what would happen to the roughness? So let's say these are sediments, and for this condition, I would say the Manning's N is 0.025. Now I am lining this channel with concrete. So what happens to the roughness? So the roughness reduces, and so if you take the roughness as 0.014 or 0.015. So if you look up Manning's N table, there could be a Manning's N value for lining of concrete, so that you can pick up. So now when we design the lined canals, what would be the key differentiator? So what principle did we use for designing canals? So 1 by n. So now what would be the key differentiator? N. So the roughness has reduced. Then what would happen to the velocity? So for lined canals we can have high velocities. Now based on this we will start an example to design a lined canal. Now somebody has designed an unlined canal. So this is a section of an unlined canal. So we don't know what is the discharge, but we know the dimensions of the canal, and this is unlined. And we want to convert this into a lined canal. So based on this given data, we have to design a lined section. So the only data we are given is the bottom width and the flow depth for a unlined canal and the side slopes. So how do we start with this data? So what information do we need for designing a canal to start with? And Q, discharge, Q. So I want to know how much water this canal is carrying, and based on this discharge, I can design a new line section. So first, based on the given data, we need to calculate what is the discharge Q. And Q is area times velocity. So is there any data that we require? So we need the longitudinal slope. So that is 0.0006. So what are the known parameters in this? A, we can calculate A for a trapezoidal section. And what about the velocity? So we use the Manning's equation to get velocity. And since this is an unlined canal, you can use N as 0.025. much is the area? Area 1.8. And the velocity? So everybody agrees with this area? So area is 1.8 or something else. .93 area. Okay, it's close. Okay, so what is the velocity? So the area that I have is 2.62. Two point 2.62. Alright, so let's use 2.62. And what is the velocity? what we got one answer 0.36. Zero point 8284. It's close. So any other velocities? Point 53. Point 52. Okay, so maybe this is right. The answer I have is 0.65. 0.65. Okay. So now what is the discharge? 1.7. So the discharge is 1.72 meter cube per second, and we need to design a channel for this discharge. So if we take the same bottom width, now we need to find what is that flow depth for a line section. So the flow depth for an unlined section is 0.91. So what would be the flow depth for a line section? Do you expect the flow depth to increase or decrease? Decrease or increase? So how many say increase? Depth. So what would happen to the depth? Depth would increase or decrease? Increase. So increase. Anybody says it is increasing? So decreasing. Yeah. So since the velocity is increasing, the depth is decreasing. Now we need to find out what this depth is. And how do we find the depth? We know the discharge and then go backwards. Yes. Yes. So this is the expression for discharge Q. Now, what are the unknowns in this? So what are the knowns? Slope is known, n is known, and anything else? Q. And what is the unknown? So A is a function of depth y, and then R is a function of y. So you have one equation and one unknown, so you solve for it and you get the depth. So you have to write an expression for area in terms of the bottom width and the depth y, and you need to do that for wetted perimeter as well. And once you have these two as a function of y, you get what is the product. Yes. So here the Manning's end is changing because this is a line section. Yes. So if you use the same Manning's end, then you will go back to the same depth. So this is a line section. So and you have to use 0.014. answers for the depth? So what is the value of depth? Y? No. But you got the area and perimeter. So the depth you should get is 0.67. So now for a light canal, the depth is 0.67 for the same bottom width. So now we are going to start on triangular section. For example, in some cases when the discharge is low, maybe you can go for a triangular section, or you can go for the usual trapezoidal section, but now we are going to consider rounded edges. So now what we are doing is sharp edges. We are going to look at rounded edges when you have triangular or trapezoidal section. Right. So let's say this is a triangular section, and now instead of having this sharp edge, in the bottom we are rounding it off. So we have a rounded corner now. And if the flow depth is y, and we are considering this an arc of a circle, so this is an arc of a circle, and we know this angle theta. And based on this, so we would be doing the same approach as here, where we know a given discharge, but now the section is different. So we have to calculate the area for a triangular section instead of trapezoidal, and then the perimeter, and use these two to get what is the flow depth y. And the side slopes is given in terms of an angle theta with respect to the horizontal. Now, what is the flow area? So this is angle theta, and then this is our total area. I'm going to divide it into two parts. So one is the area of this sector, and then we have two triangles. So that would constitute our total area. So what is this angle inside here? Let's say this is at right angles. So the sector is at right angles. So that is theta. Now what would be the total angle? So what is this angle? So this is 90 minus theta, and this inside small theta, and then here you have one more theta. So now the angle of the sector is 2 theta. So what would be the corresponding area for this sector? So for 2 pi we have an area of pi r square, and then you have 2 theta. So this would be the area for that sector. And then you need to calculate what is the area for these triangles. So what is the area of each triangle? Half base times height. So this is y. Now what would be the base? So this is my triangle, this is at right angles, so height is y. Now we need to find what is this base. So this would be y cot theta. So now we got the area, and you can also calculate what is the perimeter feet. So what would be the perimeter? Two y theta plus now both of them have become a function of the flow depth y and the side slopes theta. So if we know a given discharge q, can we calculate what is the flow depth? And I want to fix the slopes at some certain angle. Now we would get one equation like here, which is a function of y, and we have one unknown, which is y. So let's start this example. So this is our data. So we know the discharge, and then side slopes are fixed at some angle. We need to calculate what would be the flow depth for this section. And since this is a line canal, you can take n as 0.014. And what are the units for theta here? Radians. And here, degrees. So here we have two triangles, so you have to multiply by 2. So there could be another class here. So you should get a depth of 2.93. So the depth could be, you should get is 2.93. So I will upload the solution anyway. But yeah, so that's all for today. And the next class we will continue this. Who has the attendance sheet?